All right, welcome back. So for the past few explainers, we've been deep in the weeds, just trying to get data from point A to point B. But now the real chaos begins. We are moving up the stack. We're diving into part 2 of Roberto Vitillo's book, and we're about to tackle one of the absolute hardest questions in all of software. Seriously, how in the world do you get a fleet of separate, failure-prone machines to act like one single, reliable system? Well, the answer starts with something called a system model. And trust me, understanding this is the very first step to taming the chaos. I just have to start with this quote from the legend himself, Leslie Lamport. It just perfectly sums up the terrifying, interconnected world we live in as engineers. A failure on some computer you've never even heard of can totally wreck your service. Our whole job is to build systems that don't just expect this to happen, but can actually survive it.
Look, let me be blunt. If you are building a distributed system and you haven't explicitly defined your assumptions, you're just hoping for the best. That's not engineering, that's gambling. It's like trying to build a skyscraper on a foundation of quicksand. Sure, it might stand up for a little while, but you know it's going to collapse. System models are how we bring some discipline to this mess. You know, it's so easy to get complacent when you're just coding on your laptop, right? The world is simple, it's predictable, things just work. But the second you step into the world of distributed systems, you are in a completely different universe. You have to assume the network is actively trying to work against you. You have to assume a server could literally catch on fire. I'm not kidding. And that's exactly why we need models. They give us this simplified, abstract world where we can actually sit down and prove that our fancy algorithms, like Raft or Paxos, will actually hold up when things get crazy.
So how do we start to put some order on all this? We create a system model. And I really want you to think of it like this. It's your formal, binding contract with reality. It's you, as the engineer, stating exactly what kinds of chaos you're ready to handle, and maybe more importantly, what kinds you're not.
And this is not some theoretical academic thing. A system model is a super practical tool. It forces you to get specific and write down what you're assuming. Things like, okay, I'm going to assume the network can drop messages, but it won't ever corrupt them. Or maybe I'm going to assume a server that crashes can eventually come back online. Making these things explicit is the absolute non-negotiable first step to building anything that's reliable.
So let's break this down into the two main pieces. First, you've got your nodes. These are the actual computers, the processes doing the work. We usually assume they behave deterministically, but we have to accept that they can get slow and, of course, they can fail. Then you have the links, the network connecting all the nodes. And the #1 golden rule of distributed systems is this. Always, always, always assume the links are unreliable. Messages are going to get lost, they're going to get duplicated, and they're definitely going to arrive out of order. You can never, ever forget that.
And this just nails the point perfectly. It is so tempting to think, oh, all my servers are in the same building, on the same super fast switch, the network's got to be reliable. And that is such a dangerous way of thinking. A single flaky cable, a bad network card, or just a switch that's overwhelmed with traffic can introduce so much latency and packet loss that your local network feels slower than a dial-up connection to the moon. You have to design for network failure, period.
Okay, so we've got our players, our nodes and links, but now we have to face the single biggest, nastiest, most difficult problem in all of distributed systems: time. How we decide to model time is going to dictate absolutely everything else, and it determines what problems are even possible to solve.
This question is really the heart of Chapter 6 in Vitillo's book. I mean, think about it. How can you possibly figure out what's going on in your system when you have zero guarantees about time? You send a message to another server, and you hear nothing back. So what does that mean? Did the server crash? Did your message just vanish into the ether? Or is the network just having a really, really slow day? If you don't have a model for time, you're flying completely blind.
So this slide shows the two extremes, and it's really fascinating. On the left, you've got the synchronous model. This is basically a fantasy land. It's a world where you know with 100% certainty that a message will arrive within, say, 500 milliseconds. If you don't get a reply in that time, you know the other node is dead. Simple. Then, on the right, you have the asynchronous model, and this is the complete nightmare. There are 0 time guarantees. A reply might take 1 millisecond, or it might take 10 years. You literally can't tell the difference between a slow node and a dead one. And this leads to a super famous result. It is mathematically impossible to solve problems like consensus in a purely asynchronous world.
So if one model is a total fantasy and the other is an impossible nightmare, what do we actually do? Well, we use the model that pretty much all real-world systems are built on, the partially synchronous model. This is the practical, real-world compromise. We basically assume that most of the time our system is pretty well behaved and predictable. But, and this is so important, we also have to design for those moments of pure chaos when all bets are off. Think a major network outage, or a system-wide stop-the-world garbage collection pause. Our algorithms have to be tough enough to survive those asynchronous storms and get back to working correctly once things calm down.
All right, so we've modeled our world, we've modeled time. Now we have to get really specific about how we expect things to break. We need to define our fault model.
Okay, this table right here. This is fundamental. You gotta know these. Let's walk through the different flavors of failure. The simplest is crash stop. A node dies, and that's it. It's gone forever. It's easy to think about, but not very realistic. The one you'll see most often is crash recovery. This is what most web apps are built on. We assume a server can crash, but it'll probably reboot and rejoin the party even if it lost all its in-memory state. And that's why we're always persisting everything to a database, right? And then you have the final boss, Byzantine faults. This is the hardest one by far. In this model, a node isn't just dead or slow, it's actively malicious. It could be hacked, it could be buggy, and it can start lying to the other nodes to try and break the whole system. If you're building a cryptocurrency or something super secure, you have no choice but to design for this.
So the main thing I want you to take away from all this is that there's no single best model. Choosing a system model is all about engineering trade-offs. You are quite literally picking your poison. You have to balance the safety you need against performance, against complexity, and against what's even possible to build.
And this trade-off is a really delicate balancing act. If your model is way too optimistic, like you assume a perfect synchronous network, your system is just going to fall apart the first time there's a network hiccup. But if you're too pessimistic, if you assume a fully asynchronous world with evil Byzantine nodes, your system might be so complex and slow that it's useless. The real art is finding that sweet spot, like the partially synchronous crash recovery model that's tough enough for the real world, but still lets you build something that actually performs. Remember, your system model is your contract, and if you pick the wrong one, your whole system is built on a lie.
And that leads us right to the next big problem, doesn't it? It's one thing to have a model that says, okay, nodes are allowed to crash. But in a world full of network delays and weird pauses, how do you actually know for sure that a node has failed? How can you tell it apart from one that's just being really slow? Well, that's the whole challenge of failure detection, and it's exactly what we're going to break down in the very next explainer. I'll see you there.